Now we'll study some important theorems for continuous functions. Now this theorem says, if a continuous function has values of opposite sign inside an interval, then it has at least one root in that interval. So suppose this is our x-axis and we have 2 points A and B such that value of function at A and B are of opposite sign. Now case 1, when f is positive and fb is negative. Now since the function is continuous, when it goes from A to B, it will take all the values between A and B. So there will be at least one point in this interval AB, say C, such that fc is equal to 0. And if A is negative and B is positive, then also it will intersect x-axis at least at one point. There could be more than one point of intersection or more than one roots between A and B, but it will have at least one root in this interval. So this theorem is, if we have function fx in the interval AB such that fa into fb is less than 0 and this function f is continuous, that means at least one root of the equation fx equal to 0, it will lie in this interval AB. We are given this polynomial px, which is 2013 x to the power 2012 minus 2012 x to the power 2011 minus 16x plus 8. Then px equals 0 for x belongs to 0 to 8 to the power 1 upon 2011 has which of the following options. Now this 8 to the power 1 upon 2011, it is greater than 1. So what we'll do is, we'll find value of this function at 0. Value of this function at 0 is 8. Now we'll also find value of this function at 1. So value at 1 is 2013 minus 2012 minus 16 plus 8. So it'll be 1, 9. 9 minus 16 is minus 7. So from here we can say P0 into P1, it is less than 0. So at least one root will lie in 0, 1. Now we'll also find P 8 to the power 1 upon 2011. Now here what we'll do is, we'll take x to the power 2011 common. So it'll be 2013x minus 2012 minus 16x plus 8. Now x to the power 2011 will be simply 8. So it'll be 8 into 2013x minus 8 into 2012 minus 16x and then plus 8. Now here we'll take these two together. Now if we take 8x common, it'll be 2011, and here also if we take 8 common, it will be 2011. So we can write this as 8 into 2011 into x minus 1. Now since this value is greater than 1, so this value is again greater than 0. So from here we can say P1 into P 8 to the power 1 upon 2011, it is less than 0. So this equation will have at least one real root in 1, 8 to the power 1 upon 2011 using Bolzano's theorem. So this equation will have at least two real roots, and that's your option D. Now the next question is, let A, B, C be real numbers, a n equal to 0 and alpha is root of this equation. So if alpha is the root of this equation, we can write a square alpha square plus b alpha plus c equals to 0, and that's our first equation. And beta is root of the second equation. So it'll be a square beta square minus b beta minus c equals to 0, and that's our second equation. Now it says, if alpha is less than beta and both of them they are positive, then this equation, which is a square x square plus 2bx plus 2c equals to 0, has a root gamma that always satisfies. Now what we'll do is, we'll assume a function fx, which is a square x square plus 2bx plus 2c. Now since it is a polynomial function, this function is a continuous function. Now if we find f alpha will be a square alpha square plus 2b alpha plus 2c. Now b alpha plus c is minus a square alpha square. So it will be minus a square alpha square, which is less than 0. And if we find f beta, it will be a square beta square plus 2b beta plus 2c. Now b beta plus c is a square beta square. So it will be 3 times a square beta square, which is greater than 0. So from here we can say f alpha into f beta, it is less than 0. Now from Bolzano's theorem, we can say that at least one root of the equation fx equals to 0 will lie between alpha and beta, which means gamma lies between alpha and beta, and that's your option D. Now the second theorem is intermediate value theorem. It says if f is a continuous function whose domain contains the interval ab, then it takes on any given value between fa and fb at some point within the interval. Now what does that mean? Suppose again we have this x-axis and y-axis, and then we have 2 points, say a and b, and then suppose this is fa and this point is fb. Now graph of this function will start at a and then it'll take any form and finally it ends at b. Now it doesn't matter which shape it takes, but as long as this function is continuous, it will take all the values between fb and fa. So if we have any value, say fc, which lies between fa and fb, then there will be at least one point in between ab such that this function takes the value fc, and that is a intermediate value theorem. Now one important result that we generally use while solving problems is we know that fb plus fa by 2, it lies between fa and fb, and from intermediate value theorem we can say that there exists at least one point c such that fc is fb plus fa by 2, where c lies in ab. Now here the question is use intermediate value theorem to show that this equation has a solution in the interval 1 to 2. Now what we'll do is we'll take this function fx as 2x cubed plus x square minus x plus 1 in the interval 1 to 2. Now what is f1? f1 is 2 plus 1 minus 1 plus 1, it is 3. And if we find f2, f2 is 16 plus 4 minus 2 plus 1, which is 19. Now this 5, it lies between fa and fb. That means from intermediate value theorem, we can say that there exists a point c in the interval 1 to 2 such that f of x equals 5. Now here the question is prove that there exists a number x such that x to the power 200 plus 1 upon 1 plus sine square x equals 200. Now what we'll do is we'll take this as some function fx, and it'll be x to the power 200 plus 1 upon 1 plus sine square x. Now if we find f0, f0 is 1, and if we find f2, f2 will be 2 to the power 200 upon 1 plus sine square 2. Now this 200, it lies between 1 and 2 to the power 200 plus 1 upon 1 plus sine square 2. So from intermediate value theorem, we can say that there exists a point c in the interval 0 to 2 such that fx equals 200. So there exists at least one root in the interval 0 to 2. Now the theorem in continuity is Weierstrass theorem. Or extreme value theorem. Now this theorem states that if we have a function f which is continuous in closed interval ab, then this function fx, it will have a minimum value and a maximum value in this interval. In other words, we'll have 2 points, say alpha and beta, in the interval ab such that f alpha is equal to minimum value of fx when x lies between a and b, and f beta is maximum value of fx for all x between a and b, including the boundary values. So a continuous function in a closed interval will always have a minima and a maxima. So we'll always have a minima and a maxima. Now, one of the important property of continuous functions is sign preserving property. Now suppose this function fx, it is continuous at x equal to a, and this fa, it is unequal to 0. Either fa will be greater than 0 or fa will be less than 0. Then in the neighborhood of a minus delta and a plus delta, this function fx, it will be greater than 0. In the same way, if fa is negative, then in the neighborhood of a, that is in the interval a minus delta to a plus delta, fx will be less than 0. Another important result in continuous functions is if we have a function fx which is continuous in closed interval ab, then for all x in this interval ab, this integral from a to x ft dt will also be a continuous function. So basically the result is integration of a continuous function is also a continuous function. Another way to write the same result is if this function fx, it is integrable in this closed interval ab, then this integral from a to x ft dt will be a continuous function. So say for example, if we are given this integral from 1 to x sin t upon t dt, now we know that sin x upon x function, it is continuous in 1 to infinite. So this integration of a continuous function will also be a continuous function. So this integral will be a continuous function. Theorem is continuity of inverse of a function. So if you have a function fx which is defined from I to its range fi, and such that this function fx is continuous, and fx is monotonic in I, that is, it is either strictly increasing or strictly decreasing in this interval, then this f inverse, which is defined from fi to I, it will be a continuous and monotonic function. So say for example, if we have this function f, which is defined on this interval AB, such that its range is from fa to fb, and this function f is, say, strictly increasing and it is continuous, then this f inverse, which is defined from this interval from fa to fb to ab, it will also be continuous and strictly increasing. Say for example, this function f, it is defined from r to r, and this is y equals x cube, and we know graph of x cube is this strictly increasing function. And if we draw the graph of f inverse of x, and for that we'll draw this y is equal to x line and then take reflection of this graph about y is equal to x line. This is the graph of y equals x to the power 1 by 3, and it is defined on r to r. Now this function x cube, it is strictly increasing and continuous, and its inverse function f inverse, it is also strictly increasing and continuous. So that's our first theorem. Now there will be some problems in which you'll be given a function which will have piecewise definition defined separately for rational and irrational values of x. Say for example, we are given this function fx, which is f1x when x is rational, and this is f2x when x is irrational. Now we have to discuss continuity of this function fx in x belongs to r. Now if we look at any point, say x equal to a, and if we look at this limit x tends to a negative fx, that means we are talking about value of this function in the left hand neighborhood of a. Now in left hand neighborhood of a, there will be infinite rationals and infinite irrationals. So this value will oscillate between the value at rationals, which will be f1a, and the value at irrational, which is f2a. And the same way, this limit x tends to a positive fx will also oscillate between f1a and f2a in the right neighborhood of a, which again contains infinite rationals and infinite irrationals. So at each point we get an oscillating value. Now here we have two cases. Case 1, if f1a is unequal to f2a, and this second case when f1a equals f2a. Now if f1a and f2a, they are not equal, then at all these points a, we'll get two values of limits. So in that case, this limit will be oscillating. So at all such points, this function fx, it will be discontinuous. So at all the real numbers x equals a, this function will be discontinuous if f1a is different than f2a. Now if both of them are equal, in that case, both these values, they are just f1a and f1a. Now in this case, both the limits, they exist finitely and they are also equal to function value at this point. So this function fx, it will be continuous at x equal to a. Such functions are continuous at only those points where f1x equals f2x. So all we need to do is we have to equate these two definitions, and then we'll solve this equation to find real values of x, say x1, x2. So this function fx will be continuous only at these points, and at all other points this function will be discontinuous. Now say for example, we consider Dirichlet function. Now Dirichlet function is defined as 1 when x is rational and it is 0 when x is irrational. Now in this case, this one, it can never be 0. So for all a belongs to R, this limit x tends to a fx will be an oscillating value 0 and 1. So this function, it will be discontinuous in x belongs to R. So this is an example of function which is discontinuous at all the points. So there is not even a single point at which this function is continuous. Another example is, suppose we have defined this function fx as x when x is rational and 1 minus x when x is not rational. Now first we'll equate these two definitions to find the value of x. So here x is equal to 1 minus x, or value of x is 1 by 2. So this function fx is continuous at x equal to 1 by 2, and for all other points, that is for all x belongs to r minus 1 by 2, this function, it will be discontinuous.
Now question number 6 is, the function is defined by the formula fx equals x square plus 1 when x is irrational and 10x when x is rational. Now at how many values of x in the interval 0 to 4 pi, f is continuous. Now if we'll take any point, then in the neighborhood of any point, there will be infinite rationals and infinite irrationals. So that means this function will be discontinuous at all the points except for the points where the value at irrational is same as value of rational. So this function will be continuous at points where x square plus 1 is equal to 10x. So all we need to do is we need to find number of solution of this equation in the interval 0 to 4 pi. So we'll draw the graphs. So this is pi, 2 pi, 3 pi and 4 pi, and we'll draw the graph of y equals x square plus 1. So these two graphs, they intersect at 4 points. So number of points or number of values of x in the interval 0 to 4 pi where this function fx is continuous is simply 4.
Now here the question is, we are given this function fx which is x when x is rational and it is 1 minus x when x is irrational. Now it says find the continuity of f of fx. Now though it is not asked in this question, we'll discuss continuity of fx. Now literature says if we have any function fx which is defined as f1x when x is rational and f2x when x is irrational, then this function is continuous only at points where f1x equals f2x. So this function will be continuous for only those points which are solution of this equation f1x equals f2x. Now what is the reason for that? Now suppose we have this function which is defined differently for rationals and irrationals. Now at any point A, in the neighborhood of A, there will be infinitely many rationals and irrationals. So if we take its left hand limit will be this oscillating value f1a,
f2a, and on the right hand also it will be this oscillating value f1a and f2a. So both the limits on the left hand side and the right hand side, they'll be oscillating, and therefore this limit it will not exist except for the cases when it is not oscillating, and will not oscillate if both the values f1a and f2a they are equal. So that means this function is continuous for only those values where f1x must be equal to f2x. Now for this function, if we equate them, x equals 1 minus x, we'll get value of x as 1 by 2. So fx is continuous only at 1 by 2, and at all the points this function will be a discontinuous function. Now for this question, we do not need any of this analysis. So in this, what we need to do is we need to find f of fx. Now when x is rational, fx is x, and therefore this fx will be a rational number, and if fx is rational, then f of fx will be simply x. Now when x is irrational, fx is 1 minus x, and 1 minus x is irrational, and if it is irrational, it will go to this 1 minus x. Then in that case, f of fx, it will be 1 minus x, which is x. So whether rational or irrational, this fx will always going to be x. That means it is continuous for all x belongs to 0 to 1, and that's your option A. Now the question is, let A is number of points of continuity of fx, which is defined as x minus 1 when x is rational, and it is x square minus x minus 2 when x is irrational. Now we have already studied such functions, and we know that the only points where this function will be continuous is when x minus 1 is equal to x square minus x minus 2. Now we can write this as, so here we'll get 2 points. So in this case, value of A is simply 2. Now B is number of points of discontinuity of this function fx, which is signum of x cube minus 3x plus 1. Now if we look at this cubic function, which is y equals x cube minus 3x plus 1, then dy by dx is 3x square minus 1. Now it has 2 critical points, x equals plus 1 or minus 1. Now this y at 1, it will be minus 1, and y at minus 1, it will be minus 1 plus 1 will be simply plus 3. Now if we draw an approximate graph for this function, then we'll start from minus infinite, and then we'll take a positive value, and then we'll take a negative value. Now this function, it has 3 real roots. Now if this function has 3 real roots, then this signum function, it will be discontinuous at 3 points. So in this case, the value of B is simply 3. And it says C is number of points of non-differentiability of this function. Now here we have fx equals log x into mod of x minus 1, x minus 3 plus 2 into x minus 2 to the power 1 by 3. Now this mod function, it is not differentiable at 1 and 3, but at x equal to 1, this log x will be 0. So that means it is differentiable at 1. So it is non-differentiable at 3, and if we differentiate this, we get 1 by 3 and x minus 2 to the power minus 2 by 3. That means it is not differentiable at x equals 2. So value of C is 2. So this function is not differentiable at 2 points. And D is number of points where this graph has a sharp turn. Now it has a sharp turn at 3 because it is not differentiable, but at x equals 2, it actually has a vertical tangent. So in this case, value of d is simply 1. Now we need to find the value of a plus b plus c plus d. Now this is 5 plus 3, 8. So answer to this question is 8.
Now there will be some functions which will contain isolated points with no neighborhood. Say for example, we have this function fx which is defined by this under root of 1 minus x plus under root of x minus 1. Now this first expression, it is defined when 1 minus x is greater than or equal to 0, that is when x is less than or equal to 1, and the second one will be defined when x minus 1 is greater than or equal to 0 or when x is greater than or equal to 1. So this function, it is defined only at one point, x equal to 1. So if we draw the graph of this function, it will be drawn like this single point at x equals 1, and if you put x equal to 1, this value will be 0. So this is the graph of this function fx. So for this function, its entire domain is this one isolated point and there is nothing in the neighborhood, neither on the left and nor on the right. In such cases, we'll assume function to be continuous. So in this case, this function fx is supposed to be continuous at x equal to 1. So at all the isolated points where we do not have any neighborhood, function fx is assumed to be continuous. We get this result from epsilon delta definition. In this case, for every epsilon, we'll get some value of delta, and it doesn't contradict any standard condition. So such functions where we have isolated points with no neighborhood are considered to be continuous at those points. When we discuss continuity of function, we have to take into consideration continuity of individual functions. Say for example, suppose we are given this question where fx is defined as 1 upon 1 minus x, and it says find the points of discontinuity of f of fx. Now if we look at this function fx, it is defined as 1 upon 1 minus x, and this function is not defined when x is equal to 1. So this function, it has a discontinuity at x equal to 1. Now if we look at f of fx, will be 1 upon 1 minus fx. Now we'll put fx as 1 upon 1 minus x, so it will be 1 upon 1 minus 1 upon 1 minus x, which is 1 minus x upon 1 minus x minus 1. So it will be this x minus 1 upon x. Now here we have x in the denominator. So this f of fx, it is not defined when x is equal to 0. And if we look at f of fx, it will be, now we'll replace x with fx, so it will be this fx minus 1 upon fx, which is 1 upon 1 minus x minus 1 upon 1 minus x. So it will be 1 minus 1 plus x upon 1 minus x upon 1 minus x, which will cancel. So this is equal to x. So this function f of fx, it is equal to x. Now since x is a polynomial function, it appears that this function is continuous and x belongs to R. But then this function will only be defined if fx is defined and f of fx is defined. And we know that fx is not defined when x is equal to 1 and f of fx is not defined when x is equal to 0. So this f of fx, it is equal to x only when x is not equal to 0 and x is not equal to 1. So this function f of fx, it is discontinuous at x equal to 0 and x equal to 1. Now if we draw the graph of this function, y equals f of fx, it will be this graph. So this is basically y is equal to x line, but then value at 0 and 1, they are missing. So this function will be discontinuous at 2 points 0 and 1. Now when a function has removable discontinuity, we can define something called as continuous extension to a point. Now in case of removable discontinuity, both left hand limit and right hand limit, they are equal, and function value at a, either it may be missing or this value it may be isolated. Now suppose value of left hand limit and right hand limit, it is L, which is finite, then we can make this function fx continuous by defining fa equals L. So we can write this function fx as fx for whatever domain this function is defined, and this domain it won't have x equal to a, and we'll take it equal to L when x is equal to a. And when we define a function in such a way, this is called as continuous extension to a point, and now this function fx will be continuous at x equal to a. We take a very simple example. Suppose fx is defined as x square minus x minus 2 upon x minus 2 when x is unequal to 2. So this function, it has a missing point at x equal to 2, and if we define this limit x tends to 2, fx will be x square minus x minus 2 upon x minus 2, which is 0 upon 0 form. Now we can cancel this common factor in this rational function, so it will be this limit x tends to 2, and it will be x plus 1 into x minus 2 upon x minus 2. So value of this limit will be 3. Now we can make this function continuous by defining it as x square minus x minus 2 upon x minus 2 when x is unequal to 2, and we'll take it as 3 when x is equal to 2. And this function, say capital Fx, is called as continuous extension of this function fx. Now the question is, we are given this function f which is continuous on the interval 0 to 1, and it is given that f0 equals f1. Then prove that there exists a point C in 0 to 1 by 2 such that fc equals fc plus 1 by 2. Now what we'll do is, we'll let a function, say gx, which is f x plus 1 by 2 minus fx. Now since f is continuous, fx plus 1 by 2 minus fx will be a continuous function. So from here we can say this gx is a continuous function. Now if we find the value of g0, then the value of g0 will be f1 by 2 minus f0, and say this value is k. And if we find the value of g1 by 2, value of g1 by 2 will be f1 minus f1 by 2. Then the question, it says f1 is equal to f0. So it will be this minus f1 by 2 minus f0, which is minus k. And we multiply them, we can write g0 into g1 by 2 will be equal to minus k square, which is less than or equal to 0. Then from Bolzano's theorem we can say that there exists at least one c in the interval 0 to 1 by 2 such that gc equals 0. Now if we put gc equals 0, we get f c plus 1 by 2 minus fc equals 0, or fc equals fc plus 1 by 2. So we have solved this question using Bolzano's theorem. We can also solve this question using intermediate value theorem. Now here the question is, let f be a function defined on 0 to 8 to r, and it is such that f0 is 0 f4 is 1 and f8 is 1, then which of the following holds good? Now if we use Lagrange's mean value theorem on this function fx in the interval 0 to 4, we can say that there exists some point c1 in the interval 0 to 4 such that f dash c1 equals f4 minus f0 upon 4 minus 0, where c1 lies between 0 and 4. Now f dash c1, it will be f4 which is 1 and f0 is 0, so it will be 1 by 4. So there exists a point c1 in the interval 0 to 4 such that f dash c1 is 1 by 4. If it is in 0 to 4, it will also be in 0 to 8. So that means this option A, it is correct. Now if we use intermediate value theorem in the interval 0 to 4, we can say there will be some point C2 such that F4 plus F0 upon 2 equals FC2, where C2 lies in the interval 0 to 4. Now F4 is again 1, so we can write FC2, this value will be 1 by 2. Now if we multiply these two results, we can write F dash C1 into FC2 will be 1 by 8, or 8 F dash C1 into FC2 will be 1. So that means this option C is also correct. Now using the given points, it is not possible to have 12 in the denominator. So that means this option B cannot be decided from this given data. Now what about this option D? Now it says that there exists some alpha beta in the interval 0 to 2 such that this integral from 0 to 8 ft dt is equal to 3 alpha square f alpha cube plus beta square into f beta cube. Now here what we'll do is we'll assume a function gx, which is this integral from 0 to x cube ft dt. Now if we find g dash x will be fx cube into 3x square. Now what we'll do is we'll use Lagrange's mean value theorem on this function gx. First in the interval 0 to 1, we can write there exists a point g dash alpha such that g1 minus g0 upon 1 minus 0, where alpha lies in the interval 0 comma 1. And then we'll use LMBT theorem again in the interval 1 to 2, and we can write there exists a point beta in the interval 1 to 2 such that g dash beta will be equal to g2 minus g1 upon 2 minus 1. Now g dash alpha will be 3 alpha square f alpha cube and g dash beta will be 3 beta square f beta cube. So if we add them, we can write 3 alpha square f alpha cube plus 3 beta square f beta cube, and will be equal to g2 minus g0. Now g0 is 0, so this is equal to g2, and g2 is this integral from 0 to 8 ft dt. So from here we can say this integral from 0 to 8 ft dt will be equal to 3 alpha square f alpha cube plus 3 beta square f beta cube. So that means this option D is also correct. So correct options are A, C and D. Now here the question is, for a function fx equals x cos 1 by x when x is greater than or equal to 1, which of the following options are correct? Now first we'll find this limit, which is limit x tends to infinite f dash x. For that we need to differentiate this function. We'll find f dash x. Now f dash x will be x. Now derivative of cos is minus sine 1 by x, and then derivative of 1 by x is minus 1 upon x square plus, now derivative of x is 1 and then cos 1 by x. So we can write this function f dash x as 1 by x sine 1 by x plus cos 1 by x. Now if we take this limit x tends to infinite f dash x, now this is 0 and this is cos 0 and cos 0 is 1. So value of this limit is 1. That means this option B, it is correct. Now next we'll come to this option D, where we need to find whether f dash x is strictly decreasing in this interval. What we'll do is we'll differentiate this function again. We'll write f double dash x and it'll be 1 by x cos 1 by x minus 1 upon x square plus sine 1 by x as it is, and then minus 1 upon x square, and then minus sine 1 upon x and minus 1 upon x square. Now these two, they'll cancel. We'll write f double dash x as minus 1 upon x cube cos 1 by x. Since x is greater than or equal to 1, this is positive, and when x is greater than or equal to 1, 1 upon x is less than or equal to 1, which is less than pi by 2. So this cos is also positive, and then we have this negative sign. That means f double dash x is less than 0. And when f double dash x is less than 0, it simply means that f dash x is strictly decreasing function. So f dash x is strictly decreasing in the interval from 1 to infinite, and that's your option D. Now when we know f dash x is strictly decreasing, then for any x which is less than infinite, f dash x will be greater than f dash infinite. Now f dash infinite is this limit extends to infinite f dash x, which is 1. So from here we can say this f dash x is strictly greater than 1. So for any x, f dash x must be greater than 1. Now for A and C, we'll use Lagrange's mean value theorem. So if we use Lagrange's mean value theorem, we can write fx plus 2 minus fx upon x plus 2 minus x, it is equal to sum f dash c. Now we know that any derivative, it is greater than 1. So it will be greater than 1. So from here we can say fx plus 2 minus fx, it must be greater than 2, and that's your option C. So the correct options are B, C and D. Now here the question is, for every pair of continuous functions f and g such that maximum of fx equals maximum of gx, the correct statements are. Now let us say this maximum value is m, and f1 takes this maximum value at c1 and gx takes this value at c2. That means fc1 equals gc2, and it is equal to m, and this m is greater than or equal to all fx's and gx's. Now what we'll do is we'll define a function hx, which is fx minus gx. Now if we find hc1 will be fc1 minus gc1. Now fc1 is m, so this value is always greater than or equal to 0. And if we find hc2 will be fc2 minus gc2, and now gc2 is maximum value. This is always less than or equal to 0. So from here we can say hc1 into hc2 is less than or equal to 0. Thus from Bolzano's theorem we can say there exists a point C in the interval c1 and c2 which lies in the interval 0 to 1 such that hc is 0, which means such that fc minus gc is 0. So there must exist a point in the interval 0 to 1 where fc is equal to gc. Now if we look at these options, we can write this A as f square c minus g square c plus 3 fc minus gc equals 0, which is fc minus gc into fc plus gc plus 3 equals 0. And since it is 0, that means this statement A, it is correct. And if we look at not C but D, then it is fc square minus gc square will be fc minus gc into fc plus gc. Now again fc minus gc is 0. So that means this statement D is also correct. So the correct statements are A and D. Now here the question is, if B is greater than A, then we need to find location of roots of this quadratic equation x minus A into x minus B minus 1 equals 0. Now we know that coefficient of x square is positive. That means this is quadratic expression opening upwards. So the roots are alpha and beta. Now if we write this as some function fx, which is x minus A, x minus B minus 1. Now what is the value at A? fa is minus 1 and fb is also minus 1. Now since both at A and B this function takes a negative value, that means this point A, it must lie here, and B, it should lie here. That means this alpha, it should be less than A, and beta, it should be greater than B. So answer should be one root in minus infinite to A and the other in B to infinite, and that's your option D. Now here the question is, if it is given that A is greater than B, it is greater than C, it is greater than D, then prove that this quadratic equation x minus A, x minus C plus 2, x minus B, x minus D equals to 0 will have two real and distinct roots. Now what we'll do is, we'll assume a function fx, which is x minus A into x minus C plus 2 x minus B into x minus D. Now since it is a polynomial function, it is continuous function. Now if we find fa, now A minus A is 0, so it will be 2 A minus B and A minus D. Now since A is greater than B and A is greater than D, fa is greater than 0. And if we find fb, fb will be B minus A into B minus C. Now B minus A is negative and B plus C is positive, so it will be less than 0. So here we are getting this condition that fa into fb is less than 0. Then from Bolzano's theorem we can say that at least one root of fx equal to 0 will lie in the interval AB. Then the same way we'll find fc will be 2 times c minus b into c minus d. Now c minus b is negative and c minus d is positive, so it will be less than 0, and fd is d minus a into d minus c. Both of them, they are negative, that means fd is greater than 0. So from here we get this condition that fc into fd, it is less than 0. So again from Bolzano's theorem we can say that at least one root will lie in the interval CD. Now since it is a quadratic equation, it cannot have more than 2 roots. That means exactly one root will lie between A and B, and exactly one root will lie in C, D. Now here the question is, let f be a continuous function defined from 0 to 1 to 0 to 1, whose range is from 0 to 1. Then show that there exists a C in 0, 1 such that fc is equal to 1 minus c. Now what we'll do is, we'll assume a function gx, which is fx minus 1 plus x. Now since f is a continuous function, this function gx is also continuous. Now if we find g0 will be f0 minus 1, and since range of this function is from 0 to 1, this value will be less than or equal to 0. And in the same way, we can find g1, and g1 will be f1 minus 1 plus 1, which is f1, and since its range is from 0 to 1, it is greater than or equal to 0. So from here we can say g0 into g1, it is less than or equal to 0. Now from Bolzano's theorem we can say there exists a point C in 0, 1 such that GC is 0. Now if we put GC as 0, we can write FC minus 1 plus C equals to 0, or FC equals 1 minus C. Now here the question is, let f be a function defined on R to 0, 1 be a continuous function, then which of the following functions have or has the value 0 at some point in the interval 0, 1. Now if we look at the function in this option A, e to the power x minus this integral from 0 to x ft sin t dt. Now we know that when x belongs to 0, 1, e to the power x will lie between 1 and e, and ft sin t, it will lie between 0 and 1. As the value of this function lies between 0 and 1, and value of sin x also lies between 0 and 1, and thus this integral 0 to x ft sin t dt, this value will also lie between 0 and 1. Now clearly e to the power x will be greater than integral from 0 to x ft sin t dt, and therefore this gx is always greater than 0, and thus it cannot be 0. So this option A is incorrect. Now what about function in this B? So for B, let us take gx as x to the power 9 minus fx. Now what is g0? G0 is minus f0, which is less than 0, and g1 is 1 minus f1, and maximum value of f is less than 1. So this is greater than 0. So from here we can say g0 into g1 is less than 0, and thus from Bolzano's theorem we can say there exists a point C in the interval 0, 1 where gc is 0. So that means this function will have a value 0 at some point in the interval. Now for this third case, when gx is fx plus this integral from 0 to pi by 2 ft sin t dt. Now this fx is positive and this ft sin t is also positive. This gx is always greater than 0, and thus it cannot be equal to 0. So C is incorrect. Now what about this option D? Now for this option D, we'll take gx as x minus this integral from 0 to pi by 2 minus x ft cos t dt. Now again, if we find g0, g0 is minus this integral from 0 to pi by 2 ft cos t dt, and g1 will be 1 minus this integral from 0 to pi by 2 minus 1 ft cos t dt. Now this value is less than 1, and therefore g1 is greater than 0. So again from here we can say g0 into g1, it is less than 0, and from Bolzano's theorem again we can say that there is at least one root in 0, 1. So that means option D is also correct. So the correct options are B and D. Now here the question is, which of the following statements is or are correct? Now this first one is fx is greatest real function of log x plus under root of fraction part of log x. Now if we take log x as t, then we can write f e to the power t as greatest real function of t and under root of fraction part of t. Now this we have already worked out in one of the previous question. This function is continuous for all x belongs to R, so it is continuous for all t belongs to R. That is, this function is continuous for all x greater than 1. That means this statement 1 is correct. Now the statement 2 is, this limit exists and is equal to L, then we need to find the value of a plus 1 by L. Now this part B is limit x tends to minus 2, and this is 3x square plus a x plus 1 plus 1 upon, and we can factorize this as x plus 2 into x minus 1. Now this is 0, and the numerator if we put x as minus 2, it will be this 12 plus 1 13, and then minus a. Now this limit exists and is equal to L if it is an indeterminate form. That means it has to be 0 upon 0 form.
So from here we can say value of a, it should be 13. Now if we put a as 13, we can write this limit as limit x tends to minus 2. Now this is 3x square plus 13 x plus 1 plus 1, and the denominator, let this as x square plus x minus 2. Now this is 0 upon 0 form. We can use L'Hopital's rule. So it will be this limit x tends to minus 2, and this is 6x plus 13 upon 2x plus 1. Now this is 13 minus 12, 1 upon, and this is minus 3. So value of L is minus 1 by 3. Now we need to find the value of a plus 1 by L. Now a is 13 and 1 by L is minus 3. So this value is 10. That means this option B is correct. Now this third one, it says this function is defined from minus 1 to 1 to minus 1 to 1, and it is defined as fx equals x square into signum x. Now we can write this as minus x square if x is less than 0 and plus x square if x is greater than or equal to 0. Now if we draw this graph, it will be this minus x square and plus x square. Now this function, it is both 1 1 and on 2. That means this option C is also correct. And finally, for this option D, it says f is continuous on minus 1 to 1 and f minus 1 equals 4 and f1 equals 3. Now this pi, it lies between 3 and 4. Therefore, from intermediate value theorem, we can say there exists an R in the interval minus 1 to 1 such that fr must be equal to pi. That means the statement D is correct. So for this question, all the 4 statements, they are correct. Like the question is, we are given this function fx and it says if f is continuous at 0, then find the value of b. Now if we look at its right hand limit, it will be f0 positive, and it is limit h tends to 0 a plus sine 0 plus h upon h. Now get a function of sine h is 0. So it is not 0 upon 0 form, but it is 0 upon h, and 0 upon h is 0. So this is A. And as I have told you previously also, this get a function of x, it doesn't take a limiting value. It always takes an exact value. So get a function of x, it cannot approach A. It will be exactly A. So in this case, right limit is A. And if we find its left hand limit, f0 negative, it will be this limit h tends to 0. This is b plus. Now this is sine minus h. So it will be this minus sine h plus h upon, and then it will be this minus h cube. So it will be this minus h cube. Now we can write this as this limit h tends to 0, and this is b plus, and this is sine h minus h upon h cube. Now if we use the expansion of sine h, we can write this as this limit h tends to 0, this is b plus, and this is h minus h cube upon factorial 3 plus higher powers of h minus h upon h cube. Now this h and h will cancel, this h cube will also cancel. So this limit will be limit h tends to 0 b plus minus 1 by 6 plus higher powers of h. Now this value will be negative, so it will be less than 0, and get a function of 0 negative is minus 1, so it will be this b minus 1. If this function is continuous, then a must be equal to b minus 1, or the value of b is a plus 1. And that's your option B. And we can find the value of a and b also using this condition. Now here the question is, we are given this function fx, which is x plus 2 when x lies between minus 4 and 0. There is 2 minus x square when x lies between 0 and 4. We need to find f of fx, domain of f of fx, and also we need to comment upon the continuity of f of fx. Now since this is f of fx, first we'll draw the graph of fx. So we have these x's. When x is minus 4, this value is minus 2. And when x is 0, this value is plus 2. So this is minus 2 and this is plus 2. And here when x is 0, this is 2. And when x is 4, this is minus 14. So at 4, this is suppose minus 14, not to be scaled. So here this definition is x plus 2, and here this definition is 2 minus x square, and there is a definition change at this point 0. And the boundary points are minus 4 and plus 4. Now we'll draw horizontal lines at minus 4, 0 and 4. So we'll draw a horizontal line at minus 4, a horizontal line at 0, and a horizontal line at plus 4. And we'll mark these point of intersections. So we have this point, we also have this point, and then we have this point. Now we find these points. Now if x plus 2 equals 0, this point is minus 2. If 2 minus x square, it is equal to 0, then this point is root 2. And here this point is intersection of this graph, which is 2 minus x square with this line, which is minus 4. So this point is actually root 6. Now in between minus 4 and 0, definition is x plus 2. So here this definition is x plus 2. And in between 0 and 4, this definition is 2 minus x square. So now we'll start writing f of fx. So we have f of fx. Now first interval is between minus 4 and minus 2. So when x lies between minus 4 and minus 2, now since this function is continuous, again we need not bother about this equality sign. So here this definition is x plus 2, and this definition, it lies within these two lines. So this x plus 2 will go to x plus 2. So here it will be this x plus 2 plus 2. Now this next interval is between minus 2 and 0. So when x lies between minus 2 and 0, again this definition is x plus 2. Now it will go to this 2 minus x square. So it will be this 2 minus x plus 2 whole square. Now the next one is from 0 to root 2. So when x lies between 0 to root 2, definition here is 2 minus x square, and we'll go to this definition. So it will be this 2 minus x whole square. Now this next interval is between root 2 and root 6. So when x lies between root 2 and root 6, here this definition is again 2 minus x square. Now I'll go to this x plus 2. So it will be 2 minus x square plus 2. Now when x lies between root 6 and 4, we have this definition which is 2 minus x square, but then here definition of fx does not exist. So this is the only definition possible for f of fx. So we can write this as x plus 4 when x lies between minus 4 and minus 2, and it is 2 minus x plus 2 square when x lies between minus 2 and 0. This is 2 minus x whole square when x lies between 0 and root 2, and then it will be this 4 minus x square when x lies between root 2 and root 6. Now this function is defined from minus 4 to root 6. So domain of f of fx will be from minus 4 to root 6. Now since fx is continuous, its composition with itself will also be a continuous function. So this function will be continuous in its domain, which is from minus 4 to root 6. So this is our graphical method. Now we'll solve this question using algebraic method. Now for algebraic method, we have this fx, which is defined as x plus 2 when x lies between minus 4 and 0, and it is 2 minus x square when x lies between 0 and 4. Now we need to find f of fx. Now f of fx is fx plus 2 when fx lies between minus 4 and 0, and it will be 2 minus fx square when fx is greater than 0 but less than 4. Now we have two definitions of fx. So we'll split this definition in 4 parts. So now we are going to write this definition. Now first we'll take this x plus 2. So we'll put fx as x plus 2 in these two. So it will be x plus 2 when x plus 2 lies between minus 4 and 0, and this condition, which is when x lies between minus 4 and 0. And the next one is 2 minus x plus 2 square when x plus 2 lies between 0 and 4, and again it is true when x lies between minus 4 and 0. Now we have this other definition, which is 2 minus x square. So it will be this 2 minus x square plus 2 when minus 4 is less than or equal to 2 minus x square is less than or equal to 0, and here value of x lies between 0 and 4, and then we have 2 minus x square whole square when 0 is less than 2 minus x square is less than 4, and x lies between 0 and 4. Now first we'll simplify these intervals. Now here the value of x is minus 6 is less than x is less than minus 2, and here it is from minus 4 to 0. Now if we take intersection of these two conditions, we'll get the value of x between minus 4 and minus 2. So first definition is from minus 4 to minus 2, and it will be this x plus 4. Now for the second one, it will be this minus 2 and then x and then 2, and here it is from minus 4 to 0. So here common between the two is from minus 2 to 0. So next one is from minus 2 to 0, and here this definition is 2 minus x plus 2 whole square. Now in this, if we solve this, we can write this as minus 6 is less than or equal to minus x square is less than or equal to minus 2, or if we multiply with minus and take square root, it will be this x will lie between root 2 and root 6, which lies in this interval. So here this condition is the value of x should lie between root 2 and root 6. Now in this interval, value of fx is 4 minus x square. And finally, we have this, which is minus 2 is less than minus x square is less than 2. So here we'll have mod of x is less than root 2. So this is from 0 to root 2. So when x lies between 0 and root 2, this definition will be 2 minus x square whole square. Now again, it goes from minus 4 to minus 2, minus 2 to 0, 0 to root 2, and root 2 to root 6. So for this, f of fx domain is from minus 4 to root 6. Now, if we look at continuity, we'll check continuity at minus 2. So f minus 2 negative, it will be 4 minus 2, 2, and then f minus 2 positive, and since equality sign is here, so this is also equal to f2, and f2 positive will be 2 minus 0. This is 2, so it is continuous at minus 2. Now we'll check continuity at 0. f0 negative is also equal to f0, and here if we put x as 0, it will be 2 minus 4, so it will be this minus 2, and f0 positive, it will be 2 minus 4, which again is minus 2, so it is continuous at 0 also. Now we'll check its continuity at root 2. Now f of root 2 negative, now this is 0, 2, and f of root 2 will be equal to f of root 2 positive, and here it will be 4 minus 2, and it is 2. So this function is continuous in its domain. So we can find f of fx using graphical method as well as using algebraic method. Now here the question is, we are given this function fx, which is x cos 1 by x when x is greater than or equal to 1. Now which of the following options is or are correct? Now first we will find f dash x. Now f dash x will be this x, and derivative cos is minus sine 1 by x into minus 1 upon x square and plus cos 1 by x. Now here x and x will cancel, so it will be equal to 1 by x sine 1 by x plus cos 1 by x. Now we look at this option B. So if we take this limit x tends to infinite, f dash x, it will be 1 by infinite, which is 0, and plus, now this is cos 0 is 1, so this limit is 1, that means this option B is correct. Now we'll differentiate this one more time. We'll get f double dash x as 1 by x cos 1 by x into minus 1 upon x square plus sine 1 by x into minus 1 upon x square and plus this is minus sine 1 by x and then minus 1 upon x square. Now I'll cancel. So this f double dash x is minus 1 upon x cube cos 1 by x. Now when x is greater than or equal to 1, then 1 upon x will be less than or equal to 1, and this is greater than 0. Now 1 is less than pi by 2, and 0 to pi by 2, this cos x, it is positive, x is greater than 1, this is positive, and we have this negative sign, so that means f double dash x is less than 0, and if f double dash x is less than 0, that means f dash x is strictly decreasing in the interval 1 to infinite. That means this option D is also correct. Now we'll try and apply Lagrange's mean value theorem for this function in the interval x to x plus 2. We can write fx plus 2 minus fx upon x plus 2 minus x, that is equal to sum f dash x naught, where x naught lies in the interval x to x plus 2. Now, we have established that f dash x is strictly decreasing in the interval 1 to infinite. So that means any f dash x will be greater than f dash infinite, and f dash infinite we have already worked out. So any f dash x will be strictly greater than 1. So it is greater than 1. So from here we can write fx plus 2 minus fx will be greater than 2, and that means your option C is correct. So the correct options are B, C and D. And this is true for every x, because f dash x will always be strictly greater than 1 for all the values of x. Now here the question is, for every twice differentiable function f from R to minus 2 to 2, and we are given this condition that f0 square plus f dash 0 square, and it is equal to 85, which of the following statements is or are true. Now we know that codomain for this function is from minus 2 to 2. That means any value of fx will lie between minus 2 and plus 2. Now here in this case, f dash 0 is not equal to 0. And if f dash 0 is not equal to 0, then it will be either increasing or decreasing in the neighborhood of 0. So we'll always have this small interval from minus delta to plus delta, where this function will be a 1-1 function. So that means this statement 1 is always correct. Now the next one is, there exists x0 in the interval minus 4 to 0 such that mod of fx0 will always be less than or equal to 1. Now what we'll do is, we'll apply Lagrange's mean value theorem in this interval. There will be some x0 in minus 4 to 0 such that f dash x0 will be equal to f0 minus f minus 4 upon 4, and we take this mod sign. Now we know that minimum value of fx is minus 2 and maximum value is plus 2. So the maximum value of f0 minus f minus 4 will be 4. So it will always be less than or equal to 1. That means the statement B is also correct. Now this third one, it is limit x tends to infinite fx, it is equal to 1. This may not always be true. So we have this bounded function. If we can choose this bounded function fx as sum 2 sine ax, then it will satisfy all these conditions. And if we take this x tends to infinite, it will be this oscillating value from minus 2 to plus 2. And here we can also change this amplitude. We can take any value between 0 to 2. So this option C, it is not always correct. Now this D is, there exists alpha in minus 4 to 4 such that f alpha plus f double dash alpha is 0 and f dash alpha is unequal to 0. Now this option, it is the trickiest one. Now for this fourth one, what we'll do is, we'll assume a function gx, and we let this gx as fx square plus f dash x square. Now if we find g dash x, then g dash x will be 2fx into f dash x, and here it will be 2f dash x into f double dash x. Now we'll take 2f dash x common, and then we'll have fx plus f double dash x. Now if we look at g0, g0 will be f0 square plus f dash 0 square, and which is given as 85. Now what we'll do is, we'll consider two separate intervals. First interval when x lies between minus 4 and 0, and second interval where x lies between 0 and 4. Then from this statement B, we can say there exists some point x0 which lies between minus 4 and 0 such that mod of f dash x naught will be less than equal to 1. In the same way, we can prove it from 0 to 4 also. So here we'll get sum x1 lying between 0 and 4 such that f dash x1 it is less than or equal to 1. Now if f dash x naught is less than equal to 1, we can write f dash x naught square will also be less than equal to 1. Then in that case, this gx it will always be less than or equal to. Now maximum value of fx is 2, so it will be this 4 plus 1 and there will be 5. So gx naught it is less than equal to 5 and gx1 is also less than or equal to 5. Now if you look at this interval between x naught and x1 which lies between minus 4 and plus 4, this function will take some value which is less than 5 and it'll end at value which again is less than 5 and at 0 this value is 85. So this function it will increase and decrease in some way and then this value is going to come back to this lowest value. Now since this function is continuous and differentiable, there exists at least one point alpha in the interval x0 and x1 where g dash alpha it is equal to 0. Since this alpha belongs to x0, x1, it will also belong to minus 4 and 4 and then g dash alpha equals 0 means twice f dash alpha into f alpha plus f double dash alpha will be equal to 0. Now f dash alpha it cannot be 0. Now in this case this value at alpha will be maximum, so this g alpha will be f alpha square plus f dash alpha square and it should be greater than or equal to 85. Now if f dash alpha is 0, f alpha should be under root 85 but it cannot take the value greater than 2. So that means this f dash alpha it can never be 0. So the only condition that we'll get here is f alpha plus f double dash alpha it must be equal to 0. That means this option D is also correct. So the correct options are A, B and D.
Now question number 16 is, consider real valued function f satisfying fx plus 1 equals fx for all x belongs to R. That means this function is periodic with period 1. We are given that gt is this integral from 0 to t fx dx and we have defined this function ht as this limit n tends to infinite g t plus n upon n. Now if we look at gt plus n will be nothing but 0 to t plus n fx dx. Now we can write this as this integral from 0 to n fx dx plus n to n plus t fx dx. Now this function is periodic with period 1. So we can write this as n into this integral from 0 to 1 fx dx and then plus, now this is from nt to nt plus a and it will be from 0 to t fx dx. So we can write this function h as this limit n tends to infinite n this integral from 0 to 1 fx dx plus this integral from 0 to t fx dx upon n. Now we split it in two parts. This n and n will cancel and 1 upon infinite will be 0. So this ht will be nothing but will be this value from 0 to 1 fx dx which is a constant function. So this ht, it is defined for all t belongs to R and it is independent of t, and that's here option C.
Now this third question is, we are given that fx plus 1 equals 1 by 2 fx. Now let an equals from 0 to n fx dx. We need to find this limit n tends to infinite an. Now in this equation, if we put x as x plus n minus 1, then we can write fx plus n as 1 by 2 f x plus n minus 1 will be equal to 1 upon 2 square f x plus n minus 2, and using iteration it will eventually come to 1 upon 2 to the power n into fx. Now we need to find this integral an, which is from 0 to n fx dx. Now we need to find this limit n tends to infinite an, which is this summation r varies from 0 to infinite integral from r to r plus 1 fx dx. Now what we'll do is, we'll replace x with t plus r, then we can write this as this summation r varies from 0 to infinite, here will be from 0 to 1 ft plus r dt. Now using this relation we can write f t plus r as 1 upon 2 to the power r into ft. So it will be this summation r varies from 0 to infinite 1 upon 2 to the power r, then this integral from 0 to 1 ft dt. Now this is nothing but an infinite gp. Now sum of this gp will be a upon 1 minus r into this integral from 0 to 1. Now ft dt is same as fx dx. So we can write this as 2 times this integral from 0 to 1 fx dx, and that's your option D.
And question number 29, it says this gx function is defined as this integral from minus x cube to plus x cube ft dt, where ft is greater than 1 for all real t. Then we need to find which of the following option is correct. Now we are given this function gx as this integral from minus x cube to plus x cube ft dt. Now we can find g dash x, and g dash x will be fx cube into 3x square, and then minus f minus x cube into minus 3x square. Now here we can take 3x square common. We'll get fx cube plus f minus x cube. Now for this function f, it is always greater than or equal to 1. So this value, it is always greater than or equal to 2, and 3x square is always greater than or equal to 0. That means this function gx, it is strictly increasing function. Now if we consider g minus infinite, this value will be infinite minus infinite ft dt, and g infinite will be from minus infinite to plus infinite ft dt. Now since it is strictly increasing function, this value it must be negative, and this value it must be positive. And this integral from minus infinite to infinite fx dx, it approaches infinite as ft is a positive function. So this gx, it takes value from minus infinite to plus infinite, and it is strictly increasing. So if we consider this condition gx equals c, then if we draw a line at y equals c, this line, it will intersect the curve every time at one place. So answer to this question is, for any real number c, the equation gx equals to c has a unique solution, and that's your option B.
Now the question is, we are given this function fx, which is this summation r varies from 1 to n x to the power r plus x to the power minus r whole square, where x is unequal to plus or minus 1. Now we'll simplify fx. Now this is r varies from 1 to n. Now this is x to the power 2r plus x to the power minus 2r plus 2. Now this is geometric progression. It starts with x square. So this is a 1 minus r here is x square. So it will be x to the power 2n upon 1 minus x square and plus, now here in this case, first term is 1 upon x square and here will be 1 upon x to the power 2n minus 1 upon 1 upon x square minus 1 and this is plus 2n. Now we'll take this 2n on the left hand side, then we can write fx minus 2n will be this x square into 1 minus x to the power 2n upon 1 minus x square and then plus, here it will be 1 minus x to the power 2n upon 1 minus x square and then x to the power 2n. Now we can write this as x to the power 2n plus 2 plus 1 into 1 minus x to the power 2n upon, and here it will be 1 minus x square into x to the power 2n. Now it says we have defined this function gx and this gx is limit n tends to infinite fx minus 2n into x to the power minus 2n minus 2 into 1 minus x square if x is unequal to plus or minus 1 and it is minus 1 for x equals plus or minus 1. Now first we'll simplify this. Now it will be this limit n tends to infinite. Now fx minus 2n is x to the power 2n plus 2 plus 1 into 1 minus x to the power 2n upon 1 minus x square into x to the power 2n, that is multiplied with x to the power minus 2n minus 2 into 1 minus x square. Now this 1 minus x square will cancel. Now we multiply this here, we write this as limit n tends to infinite and this is 1 minus, this is 1 plus x to the power minus 2n plus 2 and here it is x to the power minus 2n minus 1. Now we have to show that this gx is continuous for all x in its domain. This region, when mod of x is less than 1, then in that case x to the power minus infinite, it will be infinite. In that case this gx, it is not defined. So gx is not defined when mod x is less than 1. Now when mod x is greater than 1, in that case x tends to minus infinite will be 0. Then this gx, it will be simply 1 into minus 1 and that is minus 1. And it is given that g plus or minus 1 is minus 1. So basically this gx, it is a constant function in its domain and therefore it is continuous in its domain.
Now question number 24 is, let f from R to R be a continuous function such that limit n tends to infinite f n x exists for every x belongs to R where f n x is composition of f n times for any n greater than or equal to 2. We have defined two sets, set S as limit n tends to infinite f n x for x belongs to R and then the set T which is fx equals x for x belongs to R. Now we'll start with this limit. Limit n tends to infinite fnx and let it be some function, say hx. Now since f is continuous, we can write this hx as f and then limit
n tends to infinite f n minus 1x. This limit n tends to infinite f n minus 1x will again be hx. So from here we can write hx is equal to f of hx, which again is of the form x equals fx when x lies in range of fx. So our set S is x equals fx for any x which lies in the range of fx. Now the set T, it is given as x belongs to R and fx equals x. Now both these sets, they look equal, but then here the crucial information is this S is when x lies in the range of fx. So essentially this S, it has to be subset of T. So answer to this question should have been S is a subset of T. ISI has given the answer as C, which is S equals T, considering x equals fx as same for both the functions. But then it is entirely up to the interpretation. Now question number 71 is, again we are given a function in two variables and we have to find its continuity and its partial derivative with respect to x. Now we'll find this limit xy tends to 0, 0. So it'll be this xy. Now we'll put xy is 0, this is 0. So this limiting value is 0, which is not equal to f 0, 0, which is given as 1. So this function is not continuous at 0, 0. Now we'll find fx at 0, 0 will be this limit h tends to 0 f h, 0 minus f0 upon h. So it will be simply this limit h tends to 0 f h0 will be 0 minus f0 is 1 upon h, and this value it tends to minus infinite. So that means this function is not continuous and partial derivative does not exist. That's your option number D. Now question number 72 is, we are given this function fx and it is given that this function is differentiable at x equal to 0. We need to find this condition. We can write this function fx as a0 cos x minus a1 sin x minus a2 x cube when x is less than 0, and it will be a0 cos x plus a1 sin x plus a2 x cube when x is greater than or equal to 0. f0 negative, it will be a0 and this is 0, so it will be a0, and f0 positive will also be a0 and the value at 0 is also a0. So this function is continuous at x equals 0. Now we'll differentiate this function. We can write this as minus a0 sin x minus a1 cos x minus 3a2 x square when x is less than 0, and it will be a0 minus sin x plus a1 cos x plus 3a2 x square when x is greater than 0. Now we'll find f dash 0 negative. F dash 0 negative will be, this is 0, this is 0, so it will be simply minus a1, and f dash 0 positive will be plus a1. Now since this function is differentiable, so minus a1 must be equal to a1. So from here we get the value of a1 should be 0. So answer to this question is, this map will be differentiable if the value of a1 is 0. Now question number 73 is, if a function fx is a differentiable function such that limit x tends to infinite fx is 1 and limit x tends to infinite f dash x is alpha, we need to find the value of alpha. Now what we'll do is, we can write f n plus 1 minus fn as fn plus 1 minus fn upon n plus 1 minus n. Now this is nothing, it is slope of this function at some point. This is equal to some f dash c where c belongs to n comma n plus 1 using Lagrange's mean value theorem. Now we'll take this limit
n tends to infinite, f n plus 1 minus fn will be this limit n tends to infinite f dash c. Now when n tends to infinite, this limit, it is equal to 1. So it is 1 minus 1, and then this limit, which is limit n tends to infinite f dash c. Now when n tends to infinite, this c also tends to infinite. So basically this n tends to infinite f dash c is nothing but alpha. So this is alpha. So from here we can say value of alpha, it must be 0, and that's your option number A. Now question number 74 is, we are given two functions such that f dash x minus g dash x is less than equal to 0 when x is less than 1, and f dash x minus g dash x is greater than equal to 0 when x is greater than 1. Now we need to find relationship between fx and gx. So we'll consider this function hx, which is fx minus gx. Then we can write h dash x as f dash x minus g dash x. Now we'll consider this first case when x is less than 1, that is when f dash x minus g dash x is less than equal to 0. So here we can say this h dash x is less than equal to 0, implying that hx is a decreasing function. Now if hx is decreasing and if x is less than 1, then hx is greater than h1. Now what is hx? Hx is fx minus gx, and it will be greater than f1 minus g1. If f1 is greater than g1, then f1 minus g1 is greater than equal to 0. So from here we can say fx must be greater than or equal to gx. So when x is less than 1, fx must be greater than equal to gx if f1 is greater than g1. Now we'll take the second case when x is greater than 1. Now when x is greater than 1, h dash x, which is f dash minus g dash, it will be greater than 0. In that case, hx will be an increasing function. So when hx is increasing, if x is greater than 1, then hx is greater than h1. Now hx is fx minus gx, and it is greater than f1 minus g1. Now f1 is greater than g1, so it is greater than equal to 0. So we can write fx is always greater than equal to gx. So for both the cases, we are getting this result, which is fx is greater than or equal to gx, and that's your option number A.
Now the question is, we are given this function fx, which is defined as greatest integral function of 10x plus under root of fraction part of 10x when x belongs to 0 to pi by 2. Now what we'll do is we'll take 10x as t. So we can write this function as y, and this is greatest integral function of t and under root of fraction part of t when t is greater than or equal to 0. Now this we have already studied. So by using graph or analytically also, this function, it is always continuous but not differentiable at integral points. So this is continuous for all t greater than or equal to 0. That means this function is continuous in 0 to pi by 2. Actually, we have solved this question thrice. First one was greatest integral function of x plus under root of fraction part of x. Second one was greater function of log x plus under root of fraction part of log x. And this third one is greater function of 10x plus under root of fraction part of 10x. All the three questions, they are essentially the same. Now here the questions, we are given this function fx, which is 23 minus 2 to the power. Now here it is minus x square plus 2x plus 3, and gx is greatest integral function of fx by mu. Now it says find the sum of all values of mu for which gx is discontinuous for at least one real value of x, and this mu is a natural number. What we'll do is first we'll find range of fx. Now if we look at this, minus x square plus 2x plus 3. So what we'll do is we'll minus 1 and add 1. So we can write this as 4 minus x minus 1 whole square. Now 4 minus x minus 1 whole square, it is always greater than minus infinite and will always be less than or equal to 4. Now if we take power of 2, then it will be 2 to the power minus infinite, and this is 2 to the power 4 minus x minus 1 square, it will be less than 2 to the power 4. Now this is 0. 2 to the power 4 minus x minus 1 whole square, that is less than 16. Now if we take a minus sign, then sign will change. So we can write this as minus 16, it is less than minus 2 to the power 4 minus x minus 1 whole square, and will be less than 0, and then we'll add 23. Now 23 minus 16 is 7. So range of this function is from 7 to 23. So value of this function fx, it will lie between 7 and 23. Fx upon mu, its greatest linear function, will be continuous if mu is greater than or equal to 23. So for all those values, this greater function will be 0. In that case, this function will always be a continuous function. So it is discontinuous at one value if mu is less than or equal to 22. That will give us 22 different values of mu. For this question, we need to find sum of all the values of mu. Now sum of all the values of mu is simply sum of first 22 natural numbers. So this is n plus 1 divided by 2. So this is 23 into 11. So this is 23 and 23, which is 253. So answer to this question is 253.